It's the first historical solution to our country's problem of apportionment, how we apportion seats in the House of Representatives to the various states. So we covered the method. We decided we liked it because it seemed pretty easy, seemed to have a fairness about it, and it made sense to us. So we left it seeming wonderful, and now we're going to examine some of the cons of Hamilton's method. There's 3 serious cons, and each of these examples is going to demonstrate one of them, and also give us a little bit of a chance to practice using Hamilton's method. Okay, so we have this small country of Calavos, 3 states, Bama, Tecos, and Illinois, total population of 20,000, and there are 200 seats to apportion in the House of Representatives. We want to determine the apportionment of that 200 seats using Hamilton's method. So in your groups, try to remember what we learned last class. Good. Seems that you don't remember. Okay. So there are 20,000 people and 200 seats, right? So how many people per seat? 100. You do 20,000 divided by 200. So we call that number the standard divisor. 20,000 divided by 200. The total number of people divided by the total number of seats. So that comes out to zeros cancel, 100 people per seat. So every 100 people in a state gets that state 1 seat in Congress. Okay, so that number is called the standard divisor. It's the first thing you calculate when doing Hamilton's method. Then you take each state's population, and we have to know how many sets of 100 it has, because for every set of 100 people, they get a seat in Congress. So we'll pull up, actually I don't need a calculator. I have to do each of these populations divided by 100. 940 divided by 100 is 9.4. 9,030 divided by 100 is 90.3. 10,030 divided by 100 is 100.3. And so my total seats, if I added those numbers up, I would get 200. Right? Giving out exactly 200 seats. But you can't give out a part of a seat. So Hamilton's method proposes the solution of giving everyone their lower quota, which would be rounding all of these down. So I would give Bama 9, Tecos 90, and Illinois 100. And when I add those up, how many seats is that? 199. Good. Good. Okay, so I have 1 left over. I have 1 surplus seat. Who should I give it to? Yeah, Bama, because they have the largest decimal part. They're the closest to earning another full seat, so we give them the extra seat. So my final apportionment is going to be 10, 9 plus the surplus, 90, 100 for 200 seats. Final apportionment. Feel refreshed? Got it? Okay. All right, so we have apportioned the 200 seats. Now, imagine that overnight, the number of seats is increased to 201. There's a secret midnight meeting of the most powerful people in the country, and they say, we're going to change it from 200 to 201, but nothing else changes. Populations are all the same. We just now have another seat to give out. Okay, so recalculate the apportionment using this new number of seats, 201 instead of 200. So don't forget, you have to start with a new standard divisor. Okay, so if we're going to do this with 201 seats, we need a new standard divisor. Total population, 20,000. Divided by the number of seats, 201, and we get 99.5. So my standard divisor changed a little bit from 100 to 99.5. So now I divide each state's population by 99.5. 100 was nice because I didn't need a calculator. Now I need a calculator. 940 divided by 99.5, 9.45. 90, 30, oops. 90.75. 100.8. And when we add those up, we should get 201. Or you'll get something super close to 201 because we did round some of these numbers as we were writing them down. You do? Okay. We must have rounded in a nice way. In this case, it doesn't matter, but when the last step is to compare the decimal parts. So you need to have enough decimals to know if this is bigger than this, right? So you might want to keep a couple just in case they agree in the 10th place. You need the 100th place to see which one is bigger. So my lower quota is now round them all down. So I get 9, 90, 100. So far I've got the exact same results with everyone's lower quotas as I did when I had 200 seats to give out. Okay, so those add up to 199, which means I have 2 left because I'm giving out 201 seats. So I should give my extra seats, my 2 surplus seats, to the states that have the largest decimal parts, right? And that would be this one and this one, Tecos and Illinois. So I give surplus here and a surplus here. So my final apportionment is going to be 9, 91, 101 to get to my 201 seats. So what do you think? I mean, try to put yourself in the shoes of each respective state. If you're Bama, okay, in the previous apportionment, you got 10 seats. And then overnight, somebody decides we have an extra seat to give out. We have more, we're actually going to have 201 and not 200. And we reapportion, and what happened to Bama? They lost a seat. We had more stuff to give out, but Bama lost a seat. Okay? It's like if we had more candy to give out and one of the kids got less candy. It seems very unfair, right? So Bama is really mad. More stuff to give out, yet they got less. Less than they did before. So this is called this is called the Alabama paradox. Okay. It happens when an increase in the number of seats to be apportioned causes a state to lose a seat. And the name comes from the 1882 apportionment of the House of Representatives. So basically, this happened to Alabama in 1882. Summary of what was being debated. They were trying to decide how many seats we should have in Congress and how we were going to apportion them. And with 299 seats, Alabama would have 8, Texas 9, and Illinois 18. Bama, Tecos, and Illinois. And then when we upped the Congress to 300 seats, it turned out that Alabama was going to lose a seat. And Texas and Illinois would both gain a seat. So Alabama just said that's totally not fair. There's more seats to give out, but we're losing a seat. So we call it the Alabama paradox. Okay. Drawback of Hamilton's method number 2. The year 2525, 5 planets in the Utopia galaxy finally signed a peace treaty and agreed to form an intergalactic federation governed by a Congress that has 50 seats in it. This is the story of the two apportionments that broke up the federation. So, in your groups, use Hamilton's method to calculate the 50-seat apportionment in the year 2525. And we have their populations, and it's 50 seats. Figure out how many seats each state gets. Okay, so let's just quickly go over the results in the first apportionment, 50-seat apportionment. So the standard quotas are, could somebody read them off for me? Well, actually, first let's do the standard divisor. We calculate that by doing the total population, 900, divided by 50 seats, which is 18 people per seat. So you divide each population by 18, and what do you get?
8.33, 12.33, 9.61, 11.33.
Great, thank you. So that should add up to 50, or very close to it, if we rounded a little. Lower quotas, round them all down. I have 8, 4, 9, 11, 16. When I add those up, what do I get? 48. So I have 2 seats to give out. I will give them to the largest decimal pieces, so that would be the 0.61 and the 0.38. So my final apportionment is going to be 8, 4, 10, 11, 17 for 50 seats. 8, 10, 11, 17. Oh, sorry, 8, 4, 10, 11, 17. Okay, so 10 years of peace pass, all is well. But then we take a census in 2535. There's some minor changes in population size. So we have the total population has grown a little bit, and Pony grew a little bit, and 204, 295. LCM grew a little bit. So everyone's grown a little, or stayed the same, or gotten a little bigger. Okay, so reapportion the 50 seats based on this new census data. Okay, let's see what happens in the reapportionment after the 2535 census. So our new total population is 909. So when I do my standard divisor, I'm going to have 909 divided by 50. 909 people divided by 50 seats comes out to 18.18 people per seat. So every 18.18 people in your state, you get a seat in Congress. So when you divide each population by the new standard divisor, what do we get? Somebody read them off. Okay, so that should add up to, if not 50, very close to 50. Yeah, just because of rounding, it might not get quite to 50. So the lower quotas, round them all down. I have 8, 4, 9, 11, 16. And when I add those up, 20, 36, 40, 48. So I have 2 surplus seats to give out. Who do they go to? Pony, because they have 0.95. And then what's the next biggest one? 2, the 0.29. Yeah, Beta. So my final apportionment is going to be 8, 4, whoops, sorry, 5, 8, 5, 10, 11, 16. Final apportionment. So what do you think? So Alanos, their population did not change. They have the same number of seats as before, right? Beta, their population did not change and they gained a seat. They're not complaining, right? Coney, their population, what happened to their population? It grew a little bit and they gained a seat. So they're like, okay, We have more people, we have another seat, makes sense. Dugos stayed exactly the same. Their population and their number of seats stayed the same. But Elysium, their population grew. Well, it could just be by one, but if this is an international federation of planets, we're probably measuring this like in millions of people. So this could have grown by 1 million, right? But if it grew by 1 or 1 million, it still grew. Yet what happened to their number of seats? They lost a seat. They have more people, fewer seats. Okay. So Elysium is really mad, right? Okay. Because there's a planet in there that had no change and gained a seat. Elysium grew and lost a seat. Okay. Elysium grew but lost a seat. Okay. This is called the population paradox. Okay, it happens if a state's population goes up, but the number of seats it is apportioned goes down. Major flaw in Hamilton's method is that this can sometimes happen. All right, third major flaw of Hamilton's method. We're going to use a non-political apportionment problem this time. We have a garbage company. It serves Northtown and Southtown. And the company has 100 garbage trucks. Apportion them using Hamilton's method. So I didn't make a table for you this time. You're going to have to do it yourself. Okay, so how many trucks are you going to send to Northtown and how many trucks are you going to send to Southtown? Okay, so let's go over it together. People are either finishing up or on their way, know what they're doing. Okay. So we have Northtown, Southtown, and total. So I'll put the population for each town. So Northtown is 10,450. Southtown is 89,550. Total is 100,000 people. So before I can start filling out the rest of the chart, remember you need a standard divisor. Okay, so my standard divisor we get by taking the total number of people and dividing by the number of trucks. 100,000 people divided by 100 trucks is 1,000 people per truck. So every 1,000 people in a town, we send one of our dump trucks there. Okay. So next we calculate standard quotas. We have to figure out how many sets of 1,000 people are in each town. So divide each town's population by 1,000 and we get 10.45 and 89.55, which adds up to 100 trucks, just like it's supposed to. But we can't send half of a truck out, so we round them all down, lower quotas, and we have 10, 89, and that's 99 trucks. So I have one truck left over. Which town should I send it to? Southtown, because they have the largest decimal. Okay, so we give them the surplus. So my final apportionment is going to be 10 to Northtown, 90 to Southtown, and that's my total of 100. Okay, so that seems relatively straightforward. Let's see what happens when the garbage company is hired by Newtown. And we have a third town now that has 5,250 homes. So to accommodate the new town, the company decides to buy 5 new trucks, right? Because for every 1,000 people, they send a truck there. So they said, okay, we'll buy 5 new trucks. That should cover this new town. And the service to our other 2 towns shouldn't be affected. 5 trucks should be enough. So carry out Hamilton's method again, now with the 3 towns, and you're now apportioning 105 trucks. Okay. So do it again and see what happens. Okay. Do apportionment. I now have Northtown, North, South, New, and total. Okay, so Northtown, that was 10,450. 89,550 for South, and Newtown is 5,250. So my new total is 105,250. So I now have a new total population and a new total number of trucks, so I need a new standard divisor. Okay, so my total population, 105,250, divided by 105 trucks, comes out to okay. Okay, so now that I have my standard divisor, I can calculate my standard quotas. Take each population and divide by the standard divisor. Can somebody read them off for me? Okay, and that should add up to a very close to, if not 105. My lower quotas, I round everything down, so I have 10, 89, 5, but that adds up to 104. And who gets the extra truck? Northtown with the 0.43. Okay, so my final is going to be 11, 89, 5 for 105 total trucks. So what do you think? Yeah, so we added a new town with their fair share of trucks. We said, okay, we're going to add 5 trucks to take care of Newtown. The apportionment gave them 5 trucks. Okay, but then it used to be that North had 10 and South had 90, and now North has 11 and South has 89. We took a truck from South and gave it to North for seemingly no good reason, right? Because we gave our 5 new trucks all to Newtown. Why should we change how many trucks the other 2 towns get? Yeah, right. So this is another paradox. So let's see, it was North gained, South lost a truck to North, which is weird, okay, because it's not like we took a truck away from North or South to take care of the new town, right? Our 5 new trucks went to take care of the new town, and then we just did some switcheroos in the 2 towns that seemed fine already. So this is called the new states paradox. It happens when the addition of a new state, or in our example, a new town, with its fair share of seats affects the apportionment of other states. So given these grievous drawbacks to Hamilton's method, we have a second historical solution proposed by Thomas Jefferson. Okay. So remember that in Hamilton's method, you divide every state's population by the standard divisor and round the result down. So up until now, everything seems fair. The funny stuff happens when we decide who the extra seats should go to. That's when all the paradoxes happened, is trying to figure out who should get those extra seats. Because it's those extra seats that make the paradoxes happen, where states can lose a seat or gain a seat. Because in one case, they got one of the surplus, and then when we changed something small, the surplus went to somebody else. Okay. So Jefferson's idea is to tweak the divisor. He says, what's so special about the standard divisor? Let's change that number a little bit so that when the quotas are all rounded down, we'll have no surplus seats. There'll be nothing left over to give out. So he's going to mess with the standard divisor. Okay. So to make this idea work, we need the quotas to be slightly bigger or smaller. What do you think? If when you round them all down, you want to have the exact number of seats, yeah, you need them to be bigger. Yeah, you need them to be a little bit bigger so that when you round down, the numbers are a little bit bigger so that you don't have any surplus. It'll add up to the total 50 instead of 48 or 49. So to make a bigger sum, you need bigger numbers. So we want our quotas to be a little bit bigger. So what should we do with the divisor, right? The number you divide by. So we've got the state's population divided by a divisor, and we get an answer, right? We want that answer to be a little bit bigger, so what should we do to this divisor? Make it a little bit smaller, because it'll go in here more times if it's smaller, right? So we want the divisor to be a little bit smaller. So take the standard divisor, we make it a little bit smaller, and hopefully everything works out so there's no extra seats. Okay, so here's the Paradors Congress again. We've done this example already. Okay, I have the standard quotas all done out for you already. So remember the standard divisor is 50,000. Okay, so we took the total population, 12.5 million, divided by the number of seats, which was 250. It's not written here. It was an example from last class. And you get 50,000 people per seat. So that's the standard divisor. So we use the standard divisor to get the standard quotas. When we do the lower quotas, we round down 32, 138, 3, 41, 13, 19. And when we add those up, what do we get? 246, which is too small. We are hoping that once we do the lower quotas, we round everything down, that we'll get exactly 250, so that we won't have any extras that we have to give out. It's a trial and error process, yes. So if 50,000, the standard divisor gave a result that was too small, right? We need to make the divisor smaller. When you divide by something smaller, the answer will be bigger. So we make our next guess, we call the modified quota. We're going to guess 49,500. Just make it a little bit smaller. And so far, this is a total guess, and I'm going to show you a way to guess smartly. Let's just see what happens when I do 49,500. So we take each state's population, and instead of dividing by the standard divisor of 50,000, I'm going to divide by 49,500. So we get 33.25. And then 6,936 divided by 49,500, 140.12. $3.11. $42.24. $13.83. $19.95. Okay, so now round all these down. We call this the modified lower quota. And I get 33, 140, 3, 42, 13, 19, and when I add them up, I get 250. No surplus seats to give out. So this will be my final apportionment. Okay, so the question is, how did I come up with 49,500, right? My only guide is that I needed to choose something smaller than 50,000. Okay, so you say, okay, it has to be smaller than 50,000. I could have chosen 49,999. Would not have worked, right? There's a range of values that will work, and you have to narrow in on it using this little guide that I'll show you. So the method in general, summary, find a suitable divisor D, that's the hard part. Using D as a divisor, compute each state's modified quota, that is their population divided by your new divisor you chose D, and then give each state its lower quota, modified lower quota. So this is a little flow chart to help you with that hard step of finding the divisor D. So use the current D, so usually start with the standard divisor, okay, to find the quotas. Round down for the lower quotas, add them all up. Okay. If the sum of those guys is the number of seats in Congress, you're done. If it's not, you say, well, is it too small? Then make D smaller. Is it too big? Then make D bigger. And this is going to be a trial and error process. So we could have, back here, had the first number we tried been 49,900. It wouldn't have worked. My sum would still be too small, so I would have had to make it smaller. Make D smaller. So this is sort of a little flow chart, and I'm just going to go through how maybe we could have come up with that 49,500. So let's say I started with my standard quotas, right? I do my lower quotas, 32, 138, 3, 41, 13, 19, and it adds up to 246, which is too small, right? 246 is too small, so I want to make D smaller. Okay. So randomly guess, right? And your guess has to do with how much, like 246 is relatively far away. That's 4 extra seats. So we need to make, that's sort of a significant jump. So maybe we would guess a whole 1,000 smaller. And experience will help you with the guessing once you've done these kinds of problems a bit. So we might guess 49,000. So then you have to do each population divided by 49,000. 6, 1, 2, 3. 33.59. So I'm doing a modified quota. And 41.55. 3.14. $42.67. $13.98. And one more. $20.16. Okay, so then we round everything down to get the modified lower quota. We get 33, 141, 3, 42, 13, 20. And that adds up to what? Let's see. 33 plus 141 plus 3 plus 42. 252. Too many, right? I only have 250 seats to give out. So my sum is too big. So I need to make my divisor, what? Bigger. When the answer's too big, make the divisor bigger. That will make your answer smaller. So now we need to make D bigger. So 49,000 was too small, so we make D bigger. We try 49,500. And we know that works because we just did it. Okay. Okay, and so that's how you narrow in on it. You make a first guess, and you get closer and closer. Okay, it's a trial and error process. So take another look at the final apportionment of state B. Go back here. State B. So I just want to highlight what happened in state B. What is their standard quota? $138.72. That is the exact number of seats that they deserve in Congress, right? If you do the number of seats that they should get in proportion to their population, they should get 138.72. How many did we give them? 140. Okay. Yeah, it violates the upper quota rule. It's an upper quota violation. So we said if this is your exact fair share, the quota rule said that the only number that makes sense to give you is 138 or 139. We can't give you a piece of a seat, so we'll either give you the number just below or the number just above. But we ended up giving them 140, which is more than their fair share. So this was an upper quota violation. Oh, that's not a good color. Upper quota violation. Standard quota was 138.72, but we gave 140. More than the upper quota. So this is a drawback to Jefferson's method. Okay? It turns out that it can sometimes produce upper quota violations, strictly upper quota violations, never lower quota. And even worse, these violations consistently favor large states. Okay, so large states will always benefit from using Jefferson's method by getting more than their upper quota of seats. So that's not good. And this problem surfaced in 1832. It was one of the most heated apportionment debates in history, in our history. So using Jefferson's method, New York's standard quota was 38.59, but they were apportioned 40 seats, okay? An upper quota violation. They got more than their upper quota. And that was the last year that Jefferson's method was used, okay? Because people started to question the constitutionality of the method. So two new methods were proposed as alternatives, one by John Quincy Adams and another by Daniel Webster, and we're going to study those next class.